Greetings, welcome to the video on test of goodness using the chi-squared goodness of fit test. Okay, this is a really important technique. You will see this technique in many different disciplines. Any place where you've got categorical data, like in the life sciences or in the social sciences, you need a way of testing whether or not a proposed distribution of proportions fits the data that you are seeing or not. Okay, and that's where the chi-squared goodness of fit test comes in. So let's talk about it. There's a bit of pre-work we're going to need to do here before we actually get into a problem and work with it. So first of all, let's go remind ourselves a little bit about what we mean by a test statistic. So we've seen throughout this course a general pattern in a test statistic. If you recall back in the beginning of the class, there's only one formula I'm going to make you memorize, and that's that Z is equal to X minus mu divided by sigma. In other words, some way of standardizing or making a metric, so to speak, of the distance between your observed value and the hypothesized value in units of the standard estimate, in standard estimate given by our point estimate. Okay, so this construct's based on it being able to identify the difference between a point estimate and an expected value in the null hypothesis if it was true, if the null hypothesis was true, and then standardizing those differences into units of standard error of the point estimate. So these two ideas are going to help us construct an appropriate test statistic for count data. We're going to construct the chi-squared test statistic using it, all right? So how do we construct the chi-squared test statistic? Well, it's pretty much built on that exact same idea that we had a minute ago. You have some sort of a point estimate. So we'll call that PE for your point estimate. And then you have minus from that some sort of expected value. And the expected value is given to you by the null. And that's divided by, in our case, some measurement of the standard error. Well, if you take a more advanced course in statistics and go on and learn to do a little bit more mathematics in it, you'll see that the standard error and count data is given by the expected count. And so those two numbers actually turn out to be the same. So if you take a look at the chi-squared test statistic, usually what we do is we've got some sort of square root, generally speaking, down here, because we get rid of the variance and turn it into the standard deviation. Well, notice that if I square this whole thing, I end up with what? I end up with my point estimate minus my expected value divided by the variance of the standard error. Okay, so consider that very rough, because that's kind of a rough justification of why we're squaring it. We'll talk a little bit more about why we're squaring it here in just a second, but that is the basic idea behind what we're doing. All right, so what do? Well, you take and you find your observed counts. So for each of your categories, classic example would be, say, a bag of plain M&Ms. There are different colors of M&Ms within the bag, and there is a proposed or expected amount of the different colors. You can go to Mars M&M's website, and they even have those proportions for you on the website for plain M&Ms if you'd like to go look that up. So you can take out and dump out your bag, and you can count the number of blues or the number of reds or the number of tans, and you can call those as your observed values. And so to calculate each of the pieces of the chi-squared test statistic, you take your first observed, minus from it your first expected, divide that by the first expected, and then of course we're going to square the numerator. More about the squaring in a minute. Then you add to that the observed value for your second color minus the expected numbers for your second color, quantity squared, divided by the second one, plus ... and you do this up to k times. In other words, you're going to have k different categories. Again, mathematicians can't spell, so we use k for category. And these would be, excuse me, there should have been 2's here on those. My bad, getting the numerators in, and these are k's. There we go, get that all fixed up. And so we'll have basically k terms in our sum that we're adding together. That sum is our chi-squared test statistic. Now, if you have to do that by hand, it is a pain in the tush, but fortunately, as we will see when we actually work the problem, R has a built-in function for doing this for us. It's really easy to use, which is nice, okay? Okay, so why are we squaring it? So I promised I talked about that. So squaring the differerences between the observed and the expected outcomes does two things. Any standardized differences that it squares will now be positive, which is muy bueno. We'll see that when we look at the chi-square differences. And the differences already looked unusual become even larger once we've squared them. And they said, where have we seen this before? And that's where I talked about earlier when we looked at variances. Let's move on. So the chi-square distribution, yet another distribution. So we have looked at the normal distribution. That was one of our first continuous distributions that we looked at. And then we saw its kissing cousin, the t distribution that was based on the degrees of freedom. So we've seen both the normal distribution, then we've seen that the standard normal was given by z, right? It doesn't have to be, but this is n of mu by sigma if it's not a standard normal, okay? And then we saw the t distribution, and then in the last section we just introduced ourselves to the f statistic, which was a skewed right distribution. And now we're about to take a look at yet another distribution, a distribution of possible observed chi-squared values. In other words, if I went into a population with a known proportion of each of those colors, like in the M&Ms, and did multiple samples, I would get very different chi-squared values every time I ran the test. And what we would see is that the distribution of those chi-squared observed values would have a skewed right distribution. So in all cases, they're all unimodal, but both the f and the chi-squared are going to be skewed to the right. So the shape of our chi-square distribution, and it again is going to be as with the t distribution and the f distribution, its shape is going to be based upon the degrees of freedom. The more degrees of freedom you have on the chi-square distribution, the less skewed it gets and the more normal it gets. You can see already at 9 degrees of freedom in the chi-square distribution, it's still definitely skewed right, but compared to with 2 degrees of freedom, it's getting much more bell-shaped than on the earlier distributions. Okay, so how would you use this bad boy? Well, we're going to use it when we're going to calculate p-values. That is the distribution that we would calculate our p-value in when the null hypothesis is that there are particular proportions that we are expecting to see in our distribution. The null saying that the population is broken up so that it's this proportion of browns, this proportion of tans, this proportion of greens, like we're talking about the M&Ms again. The null hypothesis is going to say, well, I don't think so. I think maybe one of those might be different, okay? Now, we can go in and actually calculate the chi-squared p-value using R. We can actually go in and use p chi-squared, just like we use pt or p norm. Or we could have used PF, but notice we didn't do that. We just let the book do that for us. But as we're going to see, there's a nice, just like the t-test, there is a nice test for the chi-square test. And so we're going to go ahead and use that, okay? So while it's important to know how to calculate a probability in a chi-square distribution for calculating a p-value, we're going to let R do the work for us. So the chi-square distribution, as in the F distribution, is a right-tailed test always. And that means our test statistic, large values of the test statistic, means stronger deviation away from the null hypothesis, which supports rejecting the null and doing public such, okay? And so large values of the test statistic will result in small p-values, will result in rejecting the null hypotheses. Small values of the test statistic will result in large values of the p-value, which will result in failing to reject the null hypotheses. That should be sounding very familiar at this point. If you're looking to get some new ink this weekend, maybe you should tattoo that on your arm, okay? All right, so as with all the rest of our tests, there are reasons we can or cannot use a particular test. Tests have conditions that they work under, and if they don't meet these conditions, then you should not use them. There'll be alternate techniques that you can use in place of them. What we're showing you in this class are the best techniques that are out there, and you hope to use them, and if you're not, you have to switch over to maybe less, not less in sense of that they're not as good, but they just don't produce as good a results perhaps as these do. Okay, so the first condition for a chi-square test is going to be independence. The second one is going to be the sample size, and the third one is you gotta have enough groups to have your degrees of freedom greater than 1, okay? Can't be equal to 1, so it's going to turn out this is the number of categories to use this. The minimum is 3, all right? So each particular scenario cell must have at least 5 expected counts or expected cases. That's important. So we're going to show in a minute how to calculate the expected counts. And those expected counts have to be 5 or bigger for each of them. If not, your sample size is too small and you need to get a larger sample size. Independence. Each case that contributes a count to the table must be independent of the other cases in the table. What that means is that the categories need to be independent from each other. There cannot be any sort of association or pairing between them. So bad juju, don't fail to check your assumptions. As with all of the tests, it is really important when you state your null and your alternate hypotheses. In process of doing that, you should be also checking your conditions. Okay, let's let the rubber hit the road here, and let's go work a problem and see if we can actually see how this stuff works. So let's go do exercise 6.39. Open source textbook. A professor using an open source introductory statistics book predicts that 60% of his students will purchase a hard copy, 25% will print it out from the web, 15% will read it online. At the end of the semester, he asks his students to fill out or complete a survey where they indicate the format of the book they used. Of the 126 students, 71 said they bought a hard copy of the book, 30 said they printed it, and 25 said they read it online. So state the hypotheses for testing the professor's whether his distribution is accurate or not. Okay, so let's talk about how we would write the hypotheses here. So again, we're going to have a null and an alternate, and the null hypotheses in this case is that the professor's proportions are the correct proportions for this population. In other words, he's got it right, and that what he's saying here is that P1, the first proportion, is equal to what? Well, that would be the proportion of people who purchase the hard copy of the book, and that's equal to 0.60, okay? And then the second proportion, P2, put a space in there, P2 is going to be equal to what? Well, he's saying that that's 25% or 0.25. In other words, the null hypothesis is giving us what the hypothesized distribution of the proportions are, okay? In other words, what proportion of purchased books, printed books, and online books I would be expecting to see in this class. In other words, this is what the prof is saying is what he thinks is the reality. And so what do you think the alternate is going to say? Well, the alternate is going to say, just like in ANOVA, it's going to say, nah, bologna and sausage, I think at least one of them differs, okay? So you'll come in and say, the alternate hypothesis here is that and this is nice because it's just like ANOVA, at least one, but it's not mean this time, it's proportion. Because what this is a calculation of is population proportions. So at least one proportion differs. Okay, cool. All right, so how many students did the professor expect to buy the book, print the book, and read the book out exclusively online? Okay, so to find expected value, or expected counts, are found by doing n times p. Okay, that's a golden rule. And you think about it, that makes total sense. If you assume that the proportion of boys and girls should be equal at birth, shown that it's actually slightly different from each other, but let's roll with it, they're the same. Then if you went in and randomly selected 100 birth records from a hospital, you would expect 50 of those births to be girls and 50 of those births to be boys. So how did you do that? Well, you took 100 times 0.5, which was the expected proportions, okay? So let's go ahead and do that for each one of these. So printed, or the hard copy. So hard copy expected is going to be equal to what? Well, the n here is 126, that's not going to change, times the predicted, excuse me, not the predicted, the expected times the expected, which is 0.06. Now you can do this in an R chunk if you want, but this is pretty straightforward arithmetic, and so I just did it using my calculator, okay? So, but it's up to you. If you want to put it in R chunk, please feel free to do that, and that was 75.6 is what I got there. Okay, so what do we get for the printout guys? What did the printed copies get? So the printed would be, again, 126, that's not going to change, and then that's going to be times course, you could do an inline too. I just was thinking about that. I could do an inline R here, but I've already gone this way. I'll stick with it. 0.25, and that would be equal to 31.5. And then last but not least, the online readers. What would those folks be? Well, they're going to be 126, and then again times 0.15, and that would turn out to be the expected count there is 18.9. Now you need to go through that analysis. We're actually not going to need those numbers, the 75.6, 31.5, and 18.9. We won't need those, but you need to do this to check the assumption as to whether or not they have the right sample size. In other words, each one of those expected categories has to be 5 or greater, which leads us into part C here. Is this an appropriate setting for the chi-squared test? List the conditions required for the test and verify that they are satisfied, okay? Well, so the first condition that we have to satisfy is independence. And independence is going to be satisfied here. Why? Well, we have no reason to believe that one person's purchase is influencing the other one, or to the extent that it's going to damage our data. And we know that we have less than 10% of the population. 126 is less than that. So we have no reason to disbelieve this. No reason to doubt. Dowdy. All right, so we'll roll with that. Okay, so there's no reason to doubt the independence here. Okay, so what's the second condition? Well, the second condition is the sample size condition, and we just talked about that fits. We got it. Sample size, we have that all expected values are greater than 5. And good software like RStudio will warn you if that's not true. If you try using this test and you put in data and then one of those comes out so they're not greater than 5, it'll actually throw you back an error. And the last one is that what? The degrees of freedom have to be greater than 1. And our degrees of freedom here are going to be k minus 1. So the df is equal to the number of categories minus 1, which in our case is going to be equal to 3 minus 1. We have the 3 categories, which is equal to 2, so check, that works, okay? All right, so we have verified our rules or our assumptions to use this test, and we can roll with it, okay? So now from here, they basically tell us to finish up the test of hypotheses. So we need to go through the way we've been learning how to do it in the class. So you can think about part A, B, and C here. Really, we're just getting the preliminaries, stating the null hypothesis, checking our assumptions, and now we got to get on to the rest of it. So what is the rest of it? Well, we're going down now to part 2 of a hypothesis test for us, which is a decision rule. And when you do a hypothesis test for me, I really want to see these steps. I want to see all these pieces. I want you to have thought deeply about it. And so if you stop and touch each one of these ideas, there's a good chance that you're going to not just glazed over it and thought about what the heck you're doing, okay? So our decision rule is going to be reject the null if the p-value is less than 5%. We'll roll with the gold standard here, okay? So what's the third part of a test of hypotheses? So the third part of a test of hypotheses is to give the test statistic and p-value. Okay, well, how do we do that? Well, we could, as in our last cases, we've had to do quite a bit of hand calculation, but we're not going to do that. We're going to do an R chunk, and we're going to let R actually do all the work for us here. As it turns out, there is a chi-squared test. So let's go down to the console for just a minute, and let me show you how to check on that in case you forget how to use it. It's the chi-squared test. So I did a question mark on next to that, hit an enter, and there you go. And you enter in basically the two things you have to enter in are x and p. X being the observed values and p being the proportions that are given to you in the null. So you can think about is x is observed, p is expected. So we need to generate both of those vectors. So we're going to come in here and go x equals see, and we need to go in and put in the observed counts. So what did the faculty member actually observe? Well, we saw 71, 30, and 25 respectively. So 71, 30, and 25. So those were the number of hard copies, the number printed out, and the number read online. What was the proportions he expected to see? In other words, what was his expected? Remember, we have to do observed minus expected to do the chi-squared test statistic. This is how we're going to get it done. We're going to give R the observed values, so thereby it'll know what n is. Once it knows what n is, it's going to be able to come in here and do this expected calculation for us, and then it'll do the observed minus the expected squares divided by the expected, add them all up, give us the test statistic and the p-value, and wash our car for us, and that would be just so sweet. Okay, all right. So what we need to do now is go in and put in the hypothesized proportions, the 0.6, the 0.25, and the 0.15. So we put in the 0.6, the 0.25, and the 0.15. Okay, let's just verify those real quick, make sure I got the right numbers in there. Yeah, okay, cool. All right, so we got those two in there, and now it is very simple. You just come in and you go chi-squared. So chi-squared test, see, it's already going to let me auto-complete that for me. And we put in x, comma, and this is very important. It will not work if you don't do this. The p is what's referred to as a named variable. It's not positional. If you come over here and look at the example, you notice there's a bunch of other variables before p. And so you have to name it. So you got to put in p equals p. Don't forget that or it will not work, okay? Trust me on that. Okay, so let's go ahead and run that chunk. And notice it gives us back our chi-squared value and it gives us back our p-value. In other words, it gives us our test statistic and it gives us our p-value. Sweetness, okay? So that was like really no muss, no fuss. So a heck of a lot less work than having to do all that calculation by hand. Okay, so what is the fourth step in a hypothesis test? And that is based upon the p-value and the test statistic to make a decision. So what is our decision? Our decision here is to fail to reject the null. Why are we failing to reject the null? Well, take a look at your p-value. It's bigger than 5%, isn't it? So the p-value is greater than 5%, okay? And then last but not least, and the probably most important part of the entire hypothesis test, and that is you have to give a conclusion, okay? So they do that for us in part E. So I'm going to skip my part 5 down to part E. So notice they ask us to do it, but don't forget that that's the fifth part here, okay? So we fail to reject the null or the hypothesis that the distribution of textbooks is as stated by the professor. Okay, cool beans. All right, well, that's it. That's everything we need for this particular week's module to get everything done. So get back out there and get to work, and don't be shy about posting questions up to the discussion board.